Hello to everybody in MAP 2302. This is our first video lecture. These lectures are a continuation of our in-class lectures from before spring break. So we're picking up right where we left off, which means we're starting Chapter 7. And Chapter 7 is about the Laplace transform, so we'll begin with Section 7.2, which is the definition of the Laplace transform. Okay, so the Laplace transform, first of all, it's an operator. So we've seen operators before. An operator is really just a function, but instead of plugging numbers in and getting other numbers out, you plug a function in and you get a new function out of it. So our notation for the Laplace transform is a script L. So just in kind of a picture, you can think of it, here it is, it's an operator, so what you plug in is a function. Okay? So you plug in some f, and the Laplace transform transforms it or outputs a new function, which we denote L of f. And for whatever reason, the notation, instead of parentheses or square brackets, it's these curly brackets for the new function that comes out. And as long as it's not too confusing from context, sometimes we'll just write a capital F for the output. Also, it doesn't really matter what you use for the independent variable, but it's very common, especially in our textbook, for when you're talking about the input, F, that T is used as the independent variable, and when you're talking about the output, S is used. So, some things to understand. Let's see. What about f? So what kind of functions can you plug into it? Well, a couple of things. First of all, the domain of f should be the half line, 0, infinity. And secondly, f should be piecewise continuous. So those are the kinds of functions that you can plug in to the Laplace transform. And then I need to tell you what it actually does. So let's write this out. If I start off with a function f of t and I plug it into the Laplace transform, I'm going to get out a new function, capital F of s, and here's a formula for that. It's the integral from 0 to infinity of e to the negative st times f of t dt. And you can see on the right-hand side we have an integral. The t there is the dummy variable, so after you integrate, there's no t left, and the only thing that remains is s. So the expression on the right-hand side is an expression involving only s. And the domain, let me see, I gotta scroll here, there. The domain, so one thing here, this integral, this is an improper integral, so you'll have to dust off your Calc 2 to remember how to work with those. And remember, improper integrals, they can either be convergent or divergent. So the domain here of capital F is the set of all s that make the integral convergent. Okay, so that's the definition. And that whole thing can just be summarized in just one shorthand formula to say that L of f of s is equal to this integral. All right. L, by the way, is a linear operator. The Laplace transform of a sum is a sum of Laplace transforms. The Laplace transform of c times f is equal to c times the Laplace transform of f. So just like the differential operators we looked at before, the Laplace transform is a linear operator. Okay, let's do some examples. All right, so let's find the Laplace transform of the constant function 1. So the function which is just always equal to 1 no matter what you plug in. All right, then capital F of s, we just want to use this formula. Let me just copy down the formula. Integral from 0 to infinity of e to the negative st times f of t dt. Okay, now we'll plug in 1 for f, and we need to evaluate this improper integral. Okay. S here, inside the integral, you can regard s as a constant. We're just integrating dt. And because it is an improper integral, the very first thing we need to do is write it as a limit. It's a limit as n goes to infinity of the integral from 0 to n of e to the negative st dt. Okay. Now, we can evaluate that integral. Okay, so the antiderivative here is negative 1 over s e to the negative st, and we are going to be evaluating that from t equals 0 to t equals n. Now, I think I've mentioned this before, that when I'm doing integrals, I'm evaluating them with the fundamental theorem of calculus. Instead of just writing here this vertical bar and then a 0 n, I write t equals 0 to t equals n to remind me which of the variables was the dummy variable. That way you don't make it's an easy mistake to make, to see the 0 and the n and accidentally plug it in for s, for example. So just as a reminder of where they go, I write that t equals 0 and t equals n. Okay, let's see, then continuing here, we have the limit as n goes to infinity of, now we plug in n, negative 1 over s, e to the negative ns, plus 1 over s. All right, now we have to evaluate this limit. So what's going to happen here as n goes to infinity? Well, it's going to depend on the value of s. So if s is positive, the first term there goes to 0. So we can write this piecewise. So this is going to be 1 over s if s is positive. Now if s is 0, that expression is undefined. So we have a 0 in the denominator. And if s is negative, then negative ns is in fact positive and is going to go to infinity as n goes to infinity. And so in either case, we have that this limit does not exist. So putting that all together, we can answer the original question in the example and say that the Laplace transform of the constant function 1 is the function capital F of s equals 1 over s with the domain of the open half line 0 infinity. Okay, another example. Let's find the Laplace transform of f of t equals e to the at. Here a is just some constant. Okay. All right, so we're going to write down from the definition, capital F of s, it's the integral from 0 to infinity of e to the negative st times f of t. In this case, f of t is e to the at. Now we can combine the exponentials and write this as e to the negative s minus a times t. And just like before, you don't have to go through all that work again. It's just a new coefficient up here in the exponential, we're going to get 1 over s minus a if s minus a is positive, and does not exist if s minus a is less than or equal to 0. Zero doesn't look very good. Maybe after a while I'll get so jaded to this I won't try to fix things, but for right now I feel like fixing it. There we go. Okay, so then what can we say? Put this all together. What is the Laplace transform? F of s, it's going to be 1 over s minus a, but what's the domain? The domain, remember, is all the s so that the improper integral is convergent. So we need s minus a to be positive, so it's all s, values of s bigger than a. So it's going to be the open half line from a to infinity. All right, try another one. And these ones that we're doing, these are all very fundamental Laplace transforms that you're going to want to remember. So let's find the Laplace transform of the sine of bt. And here, b is not 0. What would happen if b were 0? So if b were 0, then that's just the sine of 0, and the sine of 0 is 0. So if b were 0, we'd be talking about the Laplace transform of the 0 function. Now you could plug that into the definition and see very easily that the Laplace transform of 0 is 0. It's also another reason, or a different way of thinking about it, is that the Laplace transform is a linear function. And all linear functions take 0 to 0. So now if b is not 0, this is not the 0 function, and then there's some interesting mathematics to do. So the Laplace transform of sine of bt, this is a function of s. So, I've lost my pen. Okay, there it is. So the Laplace transform of s is equal to, I keep losing my pen somehow, is equal to the integral from 0 to infinity of e to the negative st times f of t. All right, now this, again, this is an improper integral, so we have to first write it as a limit. So the limit as n goes to infinity of the integral from 0 to n of e to the negative st sine of bt dt. Okay, now I don't know if you remember how to get an antiderivative for an integrand of this form. It involves using integration part by parts twice, letting the original integral be called I, and then you have I on both sides, and you solve for I, and then you eventually work it out. I'm not going to go through all those details here. I'll just say, let's say we did all that. Then, what would we get as our antiderivative? We would get e to the negative st over s squared plus b squared times negative s sine of bt minus b cosine of bt evaluated from t equals 0 to t equals n. Okay, I'm going to take a break and stop my recording to check the audio, because there's some, I don't know, I'm out on the back patio and there's some, well, birds, but they're probably not distracting, but I don't know, some kind of chainsaw or something. So let me check and see how it sounds, and I'll be right back. Okay, I think it sounds fine. I moved anyway, though. It was a little distracting to me. So we're here. We've got our antiderivative through a whole bunch of work that I've omitted, and now we need to evaluate it at t equals n and t equals 0. And so let's scroll this up. So I have the limit as n goes to infinity of e to the negative sn over s squared plus b squared times negative s times the sine of bn minus b times the cosine of bn minus what I get when I plug in t equals 0. Let's try and do that in our head. If I plug in t equals 0, e to the negative st is 1, sine of bt is 0, and cosine of bt is 1. So when I plug in t equals 0, I get negative b over s squared plus b squared. I'm subtracting that, so that means plus b over s squared plus b squared. Now we want the limit as n goes to infinity. So what's going to happen there? Well, the trig functions, they have no limit. Those are just going to oscillate. But the whole expression inside parentheses is going to be bounded between, well, what its highest possible value could be absolute value of s plus absolute value of b. And the lowest that it could be is the negative of that. Whereas the e to the negative sn, if s is positive, that thing's going to go to 0. So we could use the squeeze theorem in that case on the first term. And in the end, after we've done all that, what we get is that that whole first term is going to go to 0 if s is positive. So I get b over s squared plus b squared if s is positive. And otherwise, if s is 0 or if it's negative, we're not going to have any limit there. If it's 0, then we're going to have oscillations, and, well, we're going to have oscillations no matter what. And the magnitude is going to grow to infinity if s is negative. So either way, we have that it does not exist if s is less than or equal to 0. Okay. So our final answer here for the Laplace transform of the sine of bt, this as a function of s is equal to b over s squared plus b squared, and the domain is all s positive. So the whole half open or positive half line. Okay, so those are fundamental examples. Here's another example. Let's find the Laplace transform of a function f of t which is given to us piecewise. So it equals 2 if t is between 0 and 5. It equals 0 if t is between 5 and 10. And it equals e to the 4t if t is bigger than 10. Now this function is actually not defined at 5, and it's not defined at 10. And in the beginning I said that the function you plug into the Laplace transform should be defined on all of 0 infinity. So on the surface it looks like this is a problem. It's actually not a problem. I was just being a little sloppy in what I was saying. It's okay for it to not be defined at these isolated points because the integral that defines the Laplace transform is still going to make sense. So that part of the definition of f is not a problem. All right, so let's write down our definition. Capital F of s is equal to the integral from 0 to infinity of e to the st times f of t dt. All right, now we can plug in, well, we can't really plug in what f is because f is given to us piecewise. We're going to have to first break this integral down into pieces. So first we've got the piece from 0 to 5. So we'll have the integral from 0 to 5, and then we'll plug in what f is on that interval. F is equal to 2 there, so I have 2 times e to the negative st. Okay, then the next piece. Well, the next piece would be 5 to 10, but f is equal to 0 there. When you integrate 0, you just get 0, so we can skip that piece. So the final piece would be as t goes from 10 to infinity. And then what do we have? We have e to the negative st, and then f is e to the 4t. And this integrand can be simplified to be written as e to the negative s minus 4 times t. Okay. So now we have to evaluate those two integrals. The first one is just an ordinary integral, so we can get our antiderivative, which is negative 2 over s times e to the negative st, evaluated from t equals 0 to t equals 5. But the second one is an improper integral, so I have to write that as the limit as n goes to infinity of the integral from 10 to n. I'm going to do that integral here all in this same step. So for my antiderivative, I've got negative 1 over s minus 4 times e to the negative s minus 4 times t. And then we're evaluating that from t equals 10 to t equals n. So now we start plugging in some of these t values. So I have negative 2 over s times e to the negative 5t minus the same thing I get when I plug in t equals 0, which is negative 2 over s. So this becomes plus 2 over s. Then I have plus the limit as n goes to infinity. And when I plug in n, I'm going to have negative 1 over s minus 4, e to the negative s minus 4 times n, plus 1 over s minus 4, e to the negative 10 times s minus 4. Now we want to let n go to infinity. Let's see what happens. So as n goes to infinity, the exponential that has the n in it is going to go to 0 when s is bigger than 4. So if s is bigger than 4, this limit is negative 2 over s e to the negative 5t plus 2 over s plus, let me scroll up here, plus 1 over s minus 4 times e to the negative 10 times s minus 4. So that's true when s is bigger than 4. When s equals 4, this thing is undefined. We're dividing by 0. And when when s is less than 4, then the exponential that has the n in it, that thing goes to infinity. And so in either case, we have that the limit does not exist if s is less than or equal to 4. So putting that all together, my Laplace transform f of s is equal to what? Well, let's see. The first two terms I can factor out at 2 over s and write it as 1 minus e to the negative 5t, just to simplify it a little bit. And then I've got this other term, which I can write as e to the negative 10 times s minus 4 over s minus 4. And the domain of my Laplace transform is every number bigger than 4. So it's the open half line from 4 to infinity. All right, let's, I know that was not a lot of content. I think in part I'm going a little slow. It's trying to get used to this video making process. But let's stop this video part right here. So this is the end of part 1. I'm going to look at it, see how it is, and then I'll get to work on part 2. See you then.